Hey, what's up, guys? Chung here again. So this time let's take a look at another LeetCode problem here. Number 837, new 21 game. Very, it's a very good problem. I like it. So even though it's a medium problem, but I think it's a little bit underrated for a medium. I think it's more like a medium to hard problem. So let's take a look. What's what's the description here? So Alice starts with 0 points and she can draw numbers while she has less than k points. During each draw, she gains an integer number of points randomly from the range 1 to w, where w is an integer. And each draw is independent because after she draws any number from this range, basically she will pick the card back. So the next time, each time, each time's draw probability is the same. And Alice stops drawing numbers like when she gets K or more points. And then ask you what's the probability that she has N or less points. Okay. So at the beginning, I think by reading this like description, I think you might get confused because we have one, we have W, and then this part I kind of understand. But then in the end, we're being asked what's the probabilities of N or less, right? So we have three variable parameters here, input here. How can we use them? So let's take them one by one, all right? And if you guys must have already learned what the probability is, right? And then if you guys already forgot, let's take a quick look here. Uh, let's define like a DP method, right? Let's define a DP or like the function here, right? Function of I here. Let's define the function I equals to the probability of getting ice points. All right. So what's the prob so to get to the ice point, right? Let's say we have a for example, right? For example, we have uh let's say the 1 to W is 1 to 6. Let's say we have 1, 2, 3, 4, 5, 5, and 6, right? Let's assuming the W is in this range, just to make it easy, right? And then uh, then let's say the F uh, I is equals to 8. Okay, let's say F 8, right? So what's the probability of getting 8? So if you take a look, right? So how many ways we can get to 8, right? We can draw from either 1 to 6, right? And then the last so there are like basically we'll be having 6 ways. We'll have W ways to get to 8, right? Because uh the first one is to us from 7. Yes, if the first one is 7, right? F7. Because from F7, if we draw a 1, then we get F8, right? And how about another one? Another one is F6, right? From F6, if we draw a 2, then we also get F8. So on, same thing for F5, right? And then until the last one, what's the last one? The last one is F2, right? because from F2, if we draw a 6, then we also get F8, right? Basically, we have like W ways to get to draw uh, to have 8 points in the end, right? And for each of the for each of the state here, right? The probabilities of getting each number here. So because for this one we need to get 1, and this one we get 2, 3, and in the end we get 6, right? And the probabilities to get this each of these numbers are the same, right? So what's the probability? It's the W minus 1, right? Right. So same here is W minus 1, W minus 1, right? Sorry, not W minus 1, what I'm saying. It's a it's a 1 to the wth, right? It's 1 divided by W because each of the probability of getting each number is independent. So, and since we have W ways and the total probabilities of getting to the 8, it will be summarized, will be the sum of everything, right? Sum of all the probabilities. And since each of them will be multiplied by uh, 1 divided by W, we can simply uh, summarize W out, right? So we can just do this, right? And we do a plus in between, right? So okay, so basically this is our DP functions here, right? DP like state transformation function here. Basically, I'm gonna rewrite this a little bit, right? So DPI equals to what? 1 divided by W plus dp I minus 1 plus dp. Sorry, I need dp. dp I minus 2 until dp I minus W, right? Basically, this is our dp state transformation function, right? With and basically this dp function can tells us how can we calculate the current DPI's probability, right, from previously state, right? And okay, so now let's say we have each point probability here. How can we use it, right, to get the result we need, right? So it asks us, so what's the probabilities that she can has she can get has n or less points, right? So what does this mean? It means that the final result for us is from k to n, right? Basically, because we have to get the probability of k above k first, right? Because otherwise, if the point is below k, we'll keep drawing until we reach k, right? So the probabilities we need will be dp k plus dp k plus 1 until what? Until dpn. dpn, right? So this is sum, yeah. Right. So, oh, sorry. So, and this is we're assuming, right? We're assuming this n is greater than k. I think which is the case, right? Yeah. So n is greater than k. Okay. N is greater than k. That's why we can just safely assuming this like this formula works because Uh, the question is asking us about the probabilities basically between point k and point n, right? Because we need to get k's first and then ask us the probabilities starting from k to the n, right? So once we have the dp functions here, in the end, we just do a sum from dpk to dpn. That's how we can solve this problem. Okay, so with that being said, right, let's start coding. I think with this thing there, it's safe for us to come up with the actual code here, right? Okay, let's do it. And so I'm gonna create a DP here, right? DP 0. So I'm gonna create like DP n plus 1, right? Because we at the very most we need to calculate n's probability, right? So anything that's greater than n, we don't care, right? Because we don't care about that probabilities. That's not what we need, right? And then we have dp there, and then we need a starting point, right? The 0, right? So what's the 0? 0 means basically to get 0 points, right? What's the probability to get the to get to the 0 point, right? That's 1, right? Because 1 means we don't need to draw anything, right? It's a 100% probability to get 0. Okay, then from dp1, right? Now we can do a I in range 1 to n plus 1, right? So like I said, the dpi equals to the previously case probabilities summarized together and multiplied by the 1 divided by w, right? So that's why we need to like go back. We need to go back to w. All right, we need to go back to the w range, right? So we're gonna have like j. I'll do a k here. Uh, for k in range w. All right. Basically, we need to go back to the to w uh, position, and mm, but we have a few things we want to check here, right? First is the we want to make sure because here we're gonna dp like, okay, let me finish writing this thing, dpi, right? Uh, plus uh, uh, 1 divided by w, right? And then times the dp uh, I minus k minus 1, right? Because here we need the so we need to start from the dp I minus 1, right? And then and minus k here, okay? But here I think we need to make sure, right? We need to make sure this I minus 1 minus k is not a negative, right? Otherwise we'll have like a problem, right? Basically, we simply check if the uh, if I is greater than k, okay? If I is greater than k, and then we do this, right? Or we do this, or let's say if uh, smaller. Yeah, let's just do this. Okay, this is easier. If this I minus 1 is smaller than 0, right, then we simply continue, right? How about that? It's easier to understand, right? Basic. So if this is a 0, of course we don't need it, right? Because the DP inactive doesn't exist, right? That's why we want to what we want to prevent, right? And another thing, another one, and for DP, another one is the we're doing the N here, right? Uh, so since the N could be greater than K, right? But the problem here is that once the number reaches K, we won't be drawing another number, right? For example, here, let's say the K is the K is let's say the K is 17, right? Let's say the DP the K is 17, right? So for example, this one, uh, and the N is 21. Okay, let's calculate the probability of N21. Okay, so we have a DP F21 here, right? And the window is W, right? Okay, the window is W. W is 10. So if we just follow our pattern there, right? So F21, we have like 10 ways to get to 21, right? Again, right? So the 10 ways is going to be from uh, F20, right? F20 to F19, right? And to F until F11, right? And then and then when we calculate 21, we're assuming okay, all we need is to summarize everything, and then in the end we uh, times this probability 1 divided by W, right? But will this work? So there's an issue here, right? Remember, can you get 20 to 21? Can you get from 19 to 21? No, right? Because in order to get from either 19 or 20 to 21, you need to draw a card, right? So here you need to draw a 1, here you need to draw a 2. But the problem, the description tells us once you reach K, you cannot draw a card, right? Basically, the K is 17, right? There's like 17 here, right? Basically, once you reach 17, basically everything from here, right? There's no way you can get from F17 to F20 to 21 because it does not allow you to draw another card. So that's why when we calculate the DPI here, not only we need to check uh, this range, this is easier to understand, but also we also need to check if our current if this I minus W, right, is equal or greater than K, then we also need to skip it, okay, because we can only get to 21 from this range. And that's why this is how we calculate the probabilities of F21. Make sense? Okay, cool. So that's to check the out of range. And second one is this, right? If uh, uh, oh, we have a K here, so maybe I'll use a J here just to distinguish that K. Yeah, I'll use J. J. Okay, right. And if, right, is what? It's greater or equal than k, right? Then we also continue. Two things, right? Otherwise, we just summarize them together, okay? And then in the end, we simply return what? We return the sum of the dp sum, right? The dp from k to n plus 1, right? Because this is the exclusive in the Python. I think that's pretty much it is. Let's try to run it. Yeah. Okay, this one passed. Great. Let's try to run it again. Nah. Okay, so it seems like time limit exceeded. So, but at least it tells us, right? This logic somehow it works, right? So why it's TLE, right? Because the the range of K and W is 10,000, right? And here, actually, we're getting like the time. Let's take a look at the time complexity here. Basically, the time complexity is n. The first for loop is n, right? And then the second one is W, right? But the W could also be a 10,000, right? Basically, it's going to be a n square, n times n. It's a n square time complexity, which that's why it timed out, right? So, and how can we improve this thing, right? And if you take a look at the basically, we have this seems like a sliding window, right? Because if you guys take a look, so we have a uh, x x x, right? And then we have a DPI here. We have a I here, right? So we have I here, and in order to get I, we need to get the DP of I minus 1, right? And then to dpi minus w, right? So that's how we calculate I, right? Then once we have I, we move to I plus 1, right? So to calculate I plus 1, same thing, right? Same thing, we need the probabilities from dpi to dp uh, 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 I minus w plus 1, right? Plus 1 to dpi, right? It's also a slight W size of window, right? So now it's pretty obvious that this is a sliding window problem, right? So which means every time when we reach a new I here, we don't have to always go back to the W times to get everything. We can just be maintaining a rolling sum, right? That will make this inner loop from ON to O1 because every time we just need to do to insert one from the beginning and remove one from the tail. It's a constant time, right? So that's why we can move this improve this n squared to On by using sliding window. Okay, so let's see how we can do that, right? So uh so that's why we're gonna have a running sum, okay? Running sum equals to, at the beginning it's 0, right? And we are, okay. At the beginning it's 0 and let's see. Hmm. Uh, so if at the beginning it's 0, the first sum will be basically here we need to start from 0 instead of 1 because we also need to include this 0 to our running sum. All right. Uh, do I need to do that? Let me see. Let me think. Oh no, we don't. Sorry. So this running sum is the okay. So this is like a little bit a different a variance of the running sum. So the running sum is the most of the time when we're talking about running sum, it's the running sum is the running sum and including the current value, right? For example, if there's a 1, 2, 3, 4, so let's say if I'm talking about running sum of I here, right? It means that from including the current one, right? What's the running sum? So it's going to be 1, 3, 6, 10, right? So the running sum of current I means the sum including the current number. But in this case, it's different, right? Because the running sum we're trying to maintain is the sum before the current I, right? Because we need that running sum to give us the probability that we need to calculate the current probability, right? So so that's why, from to move to the current DP, right? Let's say we move from DPI minus 1 to DPI, right? And now we're at DPI. We're at DPI. So which element we need to add to the current running sum is the DPI minus 1, right? Because that's the new head of our running sum, right? And that's why we need to have running sum plus the DPI minus 1, right? So that's our running sum, mm, and when we need to remove it, right? When we need to remove one from the tail, right? Basically, is if the I is I minus 1 minus k is uh, when we can remove if the if I from I minus 1 to I minus k. Okay, yeah, if I minus 1 minus 1 minus k is it's not it's greater than 0, it's equal or greater than 0, then we can remove because remember, so the when we start removing, right, we are removing the last one, right, from the sliding window, and the size of sliding window is W, right? That's we only need to remove it when the sliding window has grown to at least W, right? So we remove it from the mm, dp I minus 1 minus W, okay? And so again here, right, same thing, right? So before, not only we need to have a restriction of the running sum when we to remove it, same thing here, right? We have to check if I is smaller than k, right? like what we discussed before. So if it's equal or greater than k, we shouldn't include that probability. Okay, so that's this two. And all right, so since we have maintained the running sum, right, and then the DPI uh, basically will be the 1 divided by W and times running sum, right? Because we already summarized everything here. And then in the end, we still return the this DP range. Uh, cool. Let's try to run it. Uh, hmm, 0. 呃 0. Why it says 0 here? Can we you know what? I'll try to print DPI here. See what's going on. Why 0? What? All 0. Even DP by W. Oh, I see. Uh, because I'm using an integer, not a double size or a float size. That's why when we do a calculation here, it will be converted to like to the integer, which is 0. So because it's treating everything as an integer, because of integer divided by integer times integers. In Python, it will assuming you are you need an integer, and anything smaller than 0 will smaller than 1 will be treated as a 0. So I think we just need to do a 1.0 here, and then once this Python compiler says, okay, the running sum is a double, is a float type, and then it will give us the float type as well. So it's no. Mm, maybe oh here I think I minus 1 here. I think I made another mistake here. I minus 1 because we want to add I minus 1 here, not I. Hmm, works. How about this one here? If I do this, hmm, also worked. Okay, so my mistake. So sorry. I thought this one will like will make it like a 0 to 1, 1 to 0, but seems like Python, even though they're all integers, maybe I got confused with Java or C Sharp. It seems like in Python, as long as you have this like true division parameters operators here, it will automatically convert to a from integer to a float. Yeah, so in Python, it doesn't really matter if you do a 1 or 1.0. It doesn't really matter. Mm, yeah. Okay. Cool. So yeah. Anyway, so it passed, and yeah. To just do a real recap. Okay. So this video is the longest one I have ever recorded, but it's such a interesting problem. That's why I want to spend a little more time to discuss this. So basically, a few concepts here, right? The first is how can we calculate uh, the probability to get to the current point, right? We use the previously uh, probabilities, previously points probabilities times this 1 divided by W, right? Because each of them is independent. And then once we have each point's probabilities, we just need to get the probabilities, summarized probabilities from K to N, right? Because that's what we need. We have to get K first and then uh, up to N. And the third one is to calculate this the sum of the previously W probabilities. Before at the beginning we were using like a naive for loop, right? To loop through everything W length for each of the I. But that's basically time limit exceeded because it's a n square uh, time complexity, and we are wasting a lot of time looping through the same element. And then we find out it's actually it's a running sum. It's a sliding window problem. All we need to do is we just need to maintain the sum of this kth kth sliding window, right? And we just need to every time when we have a sliding window, basically that it tells us what's the total probabilities, right? The probability except for the 1 divided by W, what's the total probabilities to get to the current state I, right? And then we can just simply use that one to multiply by the 1 divided by W. That can give us the current DPI. And a few things here. And first we have to check uh, the DPI. Sorry, here. Start. The first thing to check here is to remove, right? So to remove, we want to make sure, since we're going backwards, right? We want to make sure this index is not out of bound, right? This is pretty easy to understand, and this is a little bit tricky one. To add to add more probabilities, we have to check if the ones we're going to add here is less than k, because if it reaches k, it means that we'll not draw any cards. Basically, you cannot go from this DPI to our DP. You cannot go from this DPI minus 1 to our DPI here, right? Because there's no way you can draw a card once you reach K here. So, okay, cool. I think that's pretty much I want to talk about for this problem. Yeah, it's a very interesting problem. Yeah, I like it. So it combines the probabilities plus the dynamic programming and the sliding window. See, three things combined together, then you can solve this problem. Yeah, I hope you guys enjoy watching the videos. Thank you so much and stay tuned. I'll be seeing you guys soon. Bye bye.